Everyone. Welcome to this presentation. My name is Falcone. I'm an associate professor at the University of Navarre in Spain. And as soon as I share my screen, I am going to show you our presentation to the conference, which is entitled Monitoring of Electric Buses within an Urban Smart City Environment. This is a joint collaborative work between colleagues of the Institute of Smart Cities and the Public University of Navarra in Spain. So the outline of the talk is the following. First, we're going to give some introductory remarks in relation to the smart city environment and in particular to the smart city handling within the city of Pamplona. Then we're going to provide the system description of the initial system deployment that is under study. And finally, we are going to be describing the conclusions of this work. So to start with the introduction, one of the main challenges that mankind is facing right now is to provide sustainable living environments within our cities. And this is the case because there is an increasing trend in which population is moving to denser, very dense urban areas. Actually, studies say that by 2050, over 70% of human population is going to be living in these areas. Therefore, sustainability and increasing the quality of life of these regions is going to be a very, very important task. Now, in order to make these environments sustainable, it's interesting to basically control the way in which the multiple systems that define the whole operation within a city can be optimized. And we have many different examples of these systems which are operating inside a city. We have the case, for example, of energy systems and the smart grid and handling with multiple types of energy sources. We have the case of hydric resources, for example, in the case of water resources that have to be handled in an efficient way. We have transportation systems with the paradigms of intelligent transportation systems and autonomous vehicles to control routes, to optimize the way in which fuel is handled and the way in which pollution levels in terms of acoustic pollution and particle level pollutions are decreased. Of course, we also have waste management, and here we're talking about the way in which recycling is done and separation is also done. And of course, we have systems like communication systems, which play a key role in order to provide requested connectivity in order to have a truly interactive environment. Now, within the framework, the goal that we have is to describe the implementation of a practical experience within the framework of a European project called STARDUST, in which Pamplona is one of the trial cities, in the specific case of monitoring the data that is generated by a fleet of electric vehicles. And basically, we're going to be focusing on the way in which energy consumption profiles are generated and the way in which a charge is done of these batteries in the stations and the state of the batteries in order to provide predictive maintenance and also an idea on the way in which this fleet of electric buses is handled. So as we were saying, this is within the framework of the European STARDUST project, in which there are several different aspects that are tried out within what is this framework. And as we're saying, one of these aspects is related with intelligent transportation and the use of electric vehicles within these urban transportation frameworks. Now, what we are going to be discussing in this work is basically the combination of three different elements, which is basically the structure of the electric bus and the corresponding smart grid deployed, the use of wireless communication systems in order to provide a status in real time with low cost and ubiquity of the way in which these elements are working. And this is also going to be combined within a paradigm of Internet of Things with cloud-based monitoring in order to provide these monitoring capabilities, but also inference capabilities within this framework of a smart city. So let's move on now to the system description. And basically, what we are dealing with in this specific subcase within the STARDUST project is the fact that in order to achieve smart and sustainable cities, transport electrification is one of the key hours. In order to provide this, it's interesting to understand which are the operating hours in which these vehicles are going to be working, as well as the quantity of passengers per vehicle, because we are going to be using as the end systems in order to provide transportation electric buses. Now, taking into account that there is a real problem and a challenge in terms of providing adequate charging as a function of these routes and the location of the charging points, it's interesting to perform route planning tasks in order to optimize this process. So these predictable routes and the schedules are going to basically aid in developing specific infrastructure for the charging points, terms of the charge station and their connection to the city electric distribution network. We have to take into account that it's not only about the impact of how we have to charge the batteries to provide an adequate service, it is also to prepare the grid for the potential impact as the system is increased in size. Moreover, we can design and optimize energy management algorithm for the vehicle batteries in order to improve the life and performance. It's a very well-known fact that in terms of electric vehicle handling, battery status plays a key role in providing an adequate overall service. In any case, we need advanced monitoring and communication systems in order to provide these tasks in an adequate way. Now, the specific case that we have, we take out of the different routes that are available out of the public transportation system, buses, we're going to take a specific route, which is route number 9. And route number 9 is going to employ 6 100% electrical buses. And basically the route that we're going to be employing, which is depicted in this map on the left-hand side in Google Maps, is a route that expands from the train station of the city of Pamplona to the premises of the Public University of Navarre, which is where our institution lies. So basically, what we're going to have is that between the train station and the premises of the university, we have roughly 12 kilometers of trajectory. And in order to provide service to the buses within this framework, we need 44.3 kilowatt-hour lithium tritonate batteries on each one of the buses. Now, in order to do this, the charge stations have also been designed in both of the terminals, and you can see the specifications here. Basically, we require to provide 10 kilowatt-hour trip. This means that we have 3.5 minutes of maximum charge time and 70 kilowatts average consumed power. But careful, we can have, depending on the load, almost 250 kilowatts power peak. So it's very important to parameterize and monitor adequately the load of the network to take this into account. So for this, we employ the open microgrid, which is going to be comprised of a stationary battery plus photovoltaic generation. This is going to be providing smooth power demand from the grid and optimize the energy strategies. In terms of communication, we also need to provide a reliable communication system. So out of the multiple choices that we have, we are going to be focusing basically on the use of low power wireless networks because we have a low data rate, we need high levels of ubiquity, and we want to integrate this without requiring operator-based infrastructure so it can be handled by the municipality. So in order to take this into account, we know that it is compulsory to compute the coverage capacity requirements. This is to understand, depending on the specifications of the devices, what is the maximum length that we have of our communication links. So we have performed that, and in order to do so, we're going to make use of empirical-based mechanisms because even though their precision is lower than deterministic-based, we're talking about initial calculations with a very widespread. So taking this into account, we have used conventional coverage capacity relations, taking into account different types of conventional lower type low power wireless sensor network standards, and we have computed, taking into account different types of urban scenario environments, what are going to be the losses. From what we can see, if we select the lowest sensitivity devices, which are going to be given by the Torquino, then we are capable of providing links that can be well over 2 kilometers between the access point and the electric bus, which is feasible in the case of the total area in which which we are going to be carrying on. So it is feasible to employ this type of communication. Now, once we have chosen the wireless communication system, then we are going to go to the cloud-based monitoring. Basically, it's going to be composed by multiple types of components based on the ATE framework. And basically, what we're going to have is a distributed event streaming in which we are going to define the data acquisition, the pipelines, and the integration. And here you can see the different elements employed for the acquisition, machine learning, the storage, and the visualization. So in the case of the machine learning, we're going to be doing streaming analytics, and we're going to be considering the different data sets and the transformers, estimators, and the feature vectors that are going to be obtained out of the data from the bus as well as from the surrounding environment. We're going to store this in a conventional database storage based on MySQL. And once we have this data, what we're going to do is that we're going to employ different tools based basically in Grafana in order to provide us the time series that we need and the corresponding dashboards. Not only that, we're also going to have different tools in order to perform web mapping and in order to perform location representation. So here you can see some of the results. Here you can see the specifics of the cloud infrastructure that we're going to be using in our specific case, and an example of the graphical dashboard based on out of the data of the specific test that we performed. So to conclude, in order to have sustainable urban developments, we require the adoption of smart city paradigms. And in this case, we have tested within the STARDUST project the electric bus monitoring. And as you can see, we propose electric bus and smart grid integration, the adoption of wireless LoRa-based communication, and a specific cloud-based monitoring system. Future work is going to be based on full system integration as well as further field trials. So this is all for the presentation. Thank you very much for your attention. I'll be glad to answer any questions remotely. So thank you very much. Have a nice day.